All right, before diving into details, I want to first acknowledge my collaborators, Jia from Cambridge, and Francisco Vargas from Cambridge, and Zara, and Eric Van den Yeden, and the support from Miguel, Yuanqi, and Carla. All right, so first I want to narrow down the concept a little bit because I kind of like bring up like two quite huge concepts. So I want to start with the statistical mechanics and a specific problem that in statistics people call it sampling from a anormalized density, where we have an anormalized density function defined by the energy function U, and how you want to draw samples from this the invariant distribution. If you want to build a Markov chain to sample from the invariant distribution. And what people usually do is use either run molecular dynamics, like a second order or underdamped long-driven dynamics, and run the very small time steps, or you can use detailed balance to sample from the invariant distribution. Okay, but that's not what I'm going to talk about today. As I said, I want to talk about things that are out of equilibrium. So there are also mathematical tools to characterize this, and this field in physics is usually referred to as the stochastic thermodynamics. So the idea here, I'm not a physicist either, so my take on this, or my summary on the equilibrium versus non-equilibrium would be, so in equilibrium you have this detailed balance, you don't talk about anything related to time, so you only have an invariant distribution you want to draw samples from. But for the non-equilibrium, we care about some density over the path, which is defined over like the random equivalent derivative between some path measure and, for example, the Brownian motion as a base path measure, and then you can define the density or the Onsager-Marshall functional over the path. And there we also have kind of like augmented tools. We don't have detailed balance, but we have something that's a stronger relation called time reversal. Also, this comes from also the Nielsen relation in the statistics community. And we also have the non-equilibrium equalities that associate with the equilibrium quantities, key equilibrium quantities with the non-equilibrium path sampling. I'll talk about this. This is just like, I want to give a flavor about what I intend to talk about and the tools that are there. And I think everything knows the right-hand side. In probabilistic inference, like there are also, even in the machine learning community that I'm in, so we have just pushed a lot further these days, like Bayesian inference, MCMC, measure transport, stochastic control, mean-field game, mean-field control. And there are certain concepts in the statistics community we care about that can be the physical quantities, the quantities that has physical meaning that we care about on the left-hand side, and we can talk about, for example, something more specific like the normalization constant is related to the free energy, and also we can talk about then the bias and the variance of estimator, and how can we do better. All right, so that's enough for the intro. I want to move to the talk part. So I have two parts of this talk. The first part will be kind of like the majority of the talk, and the second part I want to just showcase how the same ideas can extend to improve diffusion models with inference. And the first part I want to talk about the free energy estimation problem. So yeah, as we are in the chemistry building, I'm not sure if I can assume people know chemistry and the free energy, but I'll just review it anyways. This is kind of like a central problem in physical chemistry. People care about this quantity called free energy. So the free energy FA here is defined as you have an energy function UA, and you take the normalization, is a negative log of normalization constant of the system, and you have free energy B, FB, which is the negative log of normalization constant of the other system. And usually you care about something called the free energy difference, which is the FB subtract FA, and this would tells you anything related to the reactions and how likely the reaction is going to happen, and how competitive that reaction is compared to the others. And okay, now I want to, now you can forget anything about this. What you can just remember is something like the negative log of the normalization constant. I won't talk about anything specific to the physical meaning anymore. I want to talk about from the statistical language in terms of importance sampling. So free energy perturbation is a method from 1950s, which is essentially maybe one of the first method to quantify this using Monte Carlo method. So the idea is that I want to now, so Z is the normalization constant. So now I want to write down the free energy difference as this negative log of density, like normalization constant ratio. And now I want to keep my ZA while expanding my ZB. And now you probably know what I want to do. What I want to do is like I want to put a proposal into it, which is a constant 1. And then because I have the normalization constant ZA and the unnormalized density expression of negative UA, so I can put it at PA, the normalized density, and I have my dx, so I can do Monte Carlo samples, and then I can estimate the free energy. But yeah, you may notice this is not so good because it's importance sampling. If there's no enough overlap between UA and UB, you won't do very well. Maybe it wouldn't work. And another thing you can immediately notice is that this transformation that I showed here is not unique. In fact, another simple one is like you can go the other direction. You can have samples from PB, and then you can estimate the free energy difference in a similar way. And which Bernard noticed this in 1970s, proposed this very remarkable bar estimator. So essentially what he did, it was he formalized this extra degree freedom of this transformation to estimate free energy difference as the function g. And in the end, he showed the minimal variance estimator for free energy difference as this g taken as the Fermi function, and use an iterative algorithm to solve it. So I won't go through the detail as this is not the main part of the talk, but I will just take it as granted. And in fact, that's very important because without the bar method, because the real benefit of bar method is like as long as the two distribution has a little overlap, it can already converge. So I'm going to show more in the later. Without this, it's very hard to estimate free energy computationally. All right, now I want to, as I said, like what I showed is more like something. I still have only one marginal. I don't have any sense of time. So the main, but that's a warm up. I want to get you familiar with the free energy estimation problem. What I really want to talk about is something, the non-equivalent method to solve it, so-called the Yazeski equality. I won't write down the Yazeski equality. I want to derive in a similar manner using importance sampling in discrete time to show why is it also importance sampling method and how we can talk about the bias and the variance. And then, okay, so now I have a time dimension. So let's start with my UA and finish at UB, and I can simply do a linear interpolation of the energy, right? Over the one-dimensional T, right? And so, okay, now I want to do the same thing. Well, here, everything with a tilde means something is anormalized. So here, what is anormalized? The boundary is anormalized. So I want to denote the normalization constant I want to estimate the ratio between as some normalized like Markov transition kernel, the integral over that with an anormalized boundary, right? And then I can do the same thing. I can just kind of like pull out or expand the backward process from n to 0, and then I can insert the other directions, which is a constant 1. And then I have an importance sampling problem, but over the path space, no longer over the marginal. So this is where, this is already what I'm talking about, the non-equilibrium. But then this wouldn't help me because then how do I choose the transition kernels, right? The P forward and P backward. All right, and then I want to show you a very natural choice of this transition kernel would lead to Yazeski equality. It's actually called annealed importance sampling, which was proposed a year after the Yazeski equality was written down in 1997. So what would we consider? It's like we consider a detailed balance relation. So at each of the marginal UT, so we want to choose the transition kernels for the forward and backward that they satisfy the detailed balance relation. And then what I can do is like I can further transform this to take the log of each time steps in discrete time, and then I can expand it and teleport canceling, and in the end I have this log of the path density ratio as the sum of the energy, next step energy subtract the last step energy evaluated on the same steps, and I already used the letter W there, which this is actually work in Yazeski equality. Which now I want to write down the Yazeski equality. It's in continuous time, so work is the integral of partial T ut dt. And if you substitute everything back into the importance sampling estimator, then you have the Yazeski equality from physics. Yeah, this is not the proof. This is just some intuition, but people have done the proof. All right, and then I want to write the Yazeski equality formally. I'm going back to continuous time. So what the Yazeski equality says is like if you're running SDE, you define a chain of energy, like a curved energy that interpolate from UN and U0 and UN. And you take every single instantaneous step of that, the long-driven dynamics. Notice the U is time dependent. So you run in any step that you defined for one step, if you discretize it. And you calculate the work along all the trajectories. And then you have a symptotic unbiased estimator But here you can already notice the problem, because we know that with one step we cannot mix the energy UT, right? So our distribution that we're sampling from are always lagging behind than what we intended to be, and this will show, and the error will accumulate, and in the end it will have huge variance. Even if it's asymptotically unbiased, it doesn't help you, right? So the variance would explode. And of course, you can use the bar estimator, but again, so the variance already explode. For the non-equivalent, you also have a version of bar. It's not immediately straightforward, but you can do it after some work. All right, so then I want to go back to this importance sampling perspective, because the first 10 minutes has all been centered around this importance sampling. And then what I did here is like I just take what I had, like the definition of W and the anormalized path density ratio on the boundary, only anormalized on the boundary. And then I can normalize the boundary by multiplying exponential of negative f. So negative f is a negative log of the normalization constant. So it's a little bit of yeah, but I think you get the idea. So you can normalize the boundary, and this gives us the famous Crookes fluctuation theorem. And what this further tells us is like, because we know delta f is a constant, and we want to find the place, or we want to find an estimator where the work is equal to delta f, right? So we want the work to be equal to free energy. And in the statistical, and what Crookes fluctuation theorem told you is that you actually do know what's the dissipation, which is the KL divergence between this forward and the backward. And this is just used, the dissipation word is used more in the physics community. And so then this motivates us to find a zero variance estimator that's such that we have forward process and the backward process, that they are almost always equal. And if we discretize it, some people call this trajectory balance, but essentially just we want to find a process that connected these two distribution, and they are time reversal of each other, right? So if you discretize it, just like notice here, nothing is with tilde anymore, right? So you have two boundaries and the transition kernels. And this really motivates us to think about how do we find such time reversal for this free energy estimation. All right, so now I'm going to assume a structure of this time reversal. So the first one is a forward SD that you start with PA, draw samples from PA. And the BT term is the drift or the control. I'll just call it control here. And nabla U is the negative nabla log P. So it's a score term. I'll just refer as score term. And before showing this a process with this marginal would exist, I'll just assume it exists, because this structure satisfies the Nielsen relation, because I keep the drift and I'm adding twice of the score, which is effectively flipping my score, the sign before the score. And another interpretation on top of Yazinski equality is that you have additional drift on top of Yazinski equality. So what this drift does is actually to always push you towards mixing the UT that you define. So again, here I don't want to start with talking about how to realize it. I just want to talk about what would we do if we have a time reversal like this. And in optimality, xt always follow the exponential negative ut. But here, ut can be predefined or ut can be learned, which I will show in the next slide. All right, and on the next slide after this. Well, if we have this time reversal, actually you can. So Yazinski equality and the Crookes fluctuation theorem, both relations still holds, but you need some corrections, which I called the generalized work, W hat. This is proposed by Yazinski and Suri in 2008 with the motivation to reduce dissipation. And in 2023 and 2022 and 23, there are 2 or 3 works that can prove this from stochastic calculus or PDE, that this relation still holds. And notice here, we cannot always realize the time reversal in reality. Even if we have objective, we are trying to do so with neural network, it wouldn't work as always. But we still have the Yazinski estimator, which we are just reducing the variance of that estimator. It still holds, right? So we're not limiting to things that only work when we find the time reversal. All right, now I want to talk about how to realize this. There are actually 2 ways, there are more ways, but I'll just talk about 2 specific ways to realize this. So one way to think about this is like, I don't want to learn the score. I want to fix the score because I already know my energy on the boundary, U0 and UN. I can just have let's say just a linear curve, even if it could be bad. Let's just assume that we designed the curve of energy in some ways. Yeah, this has been proved in the same paper, proved the controlled version of the Crookes fluctuation theorem, that the uniqueness and existence of this SDE, which essentially just by using the score to kill the diffusion term, the stochastic, the Brownian motion term, and then you can use the same recipe as in continuum equation and HA equation Brownian theorem to show the uniqueness of the solution. And with this in mind, we can actually already write down objective because our favorite objective in machine learning is KL divergence, right? So then we can write the KL divergence objective so we can have some samples from X0 from the one side of boundary. Notice here, I only need samples from one boundary. And then everything is tractable if we discretize the two SDEs. U is known because I predefined. BT is what I learned. So everything is just a discrete. It's a Markov transition kernel. It's a Gaussian kernel. And I can write down this objective because the normalization constant on the boundary is constant. So when optimizing, I can drop it. Well, this is okay. This is a decent objective. But the issue with this, with always reverse KL that we use, is that we have the mode collapse issue, right? So when we transport towards the other distribution, we may miss a lot of modes. And this is real in high dimensional. I've suffered with this a lot. And the next slide is actually what we advocate in the paper to learn it. So so in the last slide I told you, so we fix the score and we learn the control. And for those of you familiar with the diffusion model, is that diffusion model fix the control that learns the score, right? So and the other way, of course, is like in this problem I don't care either the score or the control, as long as I have a transport that connecting them. So I can use this stochastic interpolant. But of course, then I need a sample from both boundaries, right? And then I can just write down a simple stochastic interpolant with Gaussian noise, linear on the boundary, on the samples from the random variables, and then I can learn the control and learn the score. And the uniqueness and existence is proved in the stochastic interpolant paper. But notice here, different from previous slides, even though the reverse KL is not that good in my opinion, but it only requires samples from one boundary, just like the one side of either the first FEP estimator or the Yazeski estimator. But here you do require samples from both boundaries, so this would be compared to the bar estimator. But in our opinion, people would use bar estimator anyways. I'm not aware of anyone actually using the FEP estimator because, yeah, that part of theory about bar is actually of independent interest. So that's how we do it, and then so that's how we train, how we learn the score, like nabla U, and how we learn the control B, right? So after it's learned, we need to then the next thing to do is like we need to calculate the work. Then how do we calculate work? There are two ways, as I showed. Yazeski has this what's called escorted density on the left-hand side, so to estimate this generalized work, and but what we advocate is using the right-hand side, to use the density ratio to estimate the work. And so to show what it gets discretized in reality is that first this P, again, there's no tilde, so it's normalized. Then I'm adding the free energy difference. I want to denormalize the boundary, which we don't know the normalization constant on the boundary anyways. And then we can discretize all this path because this path is longer one. So I can just approximate the Gaussian kernels. And there are several noticeable benefits on the right-hand side to estimate work. One is I should avoid use the word divergence phrase. It doesn't require divergence calculation, and you see the divergence is the BT. So that's kind of like in machine learning, we usually say when you have continuous normalizing flow or something, if you have a divergence of the vector field, usually it's quite expensive, or you need the Hutchinson estimator to approximate. And also, you don't need to parameterize the energy because all we need to use is score. This is more like practical because in reality, people just find energy parameterization is worse than score parameterization. And also, we don't need importance sampling on the boundary. Why? Because if you parameterize the energy, then the energy you learned on the boundary may not match the energy that you want. So you need additional importance sampling. The last thing is more like practical. So it's, you don't need a second discretization. if you want to calculate work on the left-hand side way, so you need another discretization on this ODE, right? So if you use the right-hand side, so you only discretize the SDE to draw samples, and then you evaluate on it. So you don't need a second discretization. All right, so feel free to stop me if there's question or I'm going too fast. So next, I want to show some results on this. So we done a few results, but we are still working on higher dimensional problem. The first one is our favorite Gaussian mixture models, and we put it in high dimensional with 16 modes, and the other side with 40 modes, and the Lerner-Jones potential, like the people favorite toy problems. And it's kind of like the one side of because we have two systems. One side of it is just the harmonic potential to keep particles together, and the other one is the harmonic potential plus the Lerner-Jones potential. And we also do with again our favorite toy problem, alanine dipeptide, 22 atoms, 66 degree freedom. In vacuum versus one side of it is in vacuum, the other side is in implicit solvent. Handling the solvent, explicit solvent, is another huge question for the field as well. So, and for alanine dipeptide, we can also do the transition-free energy, which we project it to the two-dimensional, what we call the collective variables or the reaction coordinates, and then we can cross out where we know the modes are, and we want to know how hard the transition happens, or how likely the transition happens. All right, then there are some numerical results. I think in summary, okay, we are comparing the reference. What we get is from a multi-state bar method, because when the two distribution has no overlap, you cannot use bar either. So you need a multi-state bar. That's what people use till today. So we compare with a few neural network-based method, which I didn't really expand what they are, but essentially the first one, target FEP. The idea is like using a normalizing flow or continuous normalizing flow to learn a change of variable from one side of the one boundary to be closer to the other boundary, and then you do the impedance sampling there, and you use what's the normalizing flow, the work that it does to help you to bridge as the proposal. And the neural TI is another method based on thermodynamic integration. So how thermodynamic integration works is like it's another method that kind of like also takes the interpolation of the energy, and at each of the energy level along the chain that you require to mix that distribution. And it's a different estimator. And why people use neural net like neural TI, because a known issue to that problem is to that method is that how do you define the interpolation of the energy? Well, people use the diffusion or stochastic interpolant to learn the energy to define it. That defines the interpolant. Essentially, here what I want to show is like solve those problems quite decently, and then of course we need to solve higher dimensional problems. And the hardest one is actually the Lerner-Jones potential with 128 particles, which is 400 dimensions. And just a little bit of something more qualitative. The figure that we can look at, you can see, here the black dashed line is the reference value, the ground truth, and the right one, the two right curves are the two-sided Yazinski estimator, and the blue one is what we use the bar estimator. You can see like it converges very fast, and the x-axis is the number of training iterations, right? So, yeah. All right, and to wrap up, as I said, I have another little part for 10 minutes maybe. But for the first part, we also apply this to, I've heard Professor Lin talk about this parallel tempering or replica exchange, Monte Carlo. So we can also apply the same work to realize non-equivalent process. The idea is that we can always bridge two distribution by taking either a continuous normalizing flow, discrete normalizing flow, a controlled SDE or a SDE. Well, we can keep track of the work, and that we can bridge the two distribution. We also apply this to, Yazinski also wrote another paper in 2009 at PNAS to use non-equivalent switches to improve parallel tempering. We also did that in another work. All right, so I'll move to the little part. The same ideas of this non-equivalent process can help us controlling an estimation better with diffusion model. So now I want to, again, write the diffusion model as a time reversal. So I have a forward, here, as I said, the control is fixed, and I'm shifting the things a little bit because in diffusion model, you only have a, let's say, OU process as your forward process. And the backward process, like where you learn the score. Yeah, what Cooch fluctuation theorem tells us is that, we don't have to think in backward, like as equality, initially the version I showed, but you can actually derive what backward process gives you that estimator, right? So it provides an extra degree of freedom as design and think about it. Or it's very easy if you're familiar with sequential Monte Carlo. It's exactly just sequential Monte Carlo. Now I want to, okay, so next I want to talk about the density estimation problem with the diffusion model. So the problem is that, we know the density of the Gaussian, but we don't know the density of the data. So we want to evaluate the data point under this diffusion model to see what's the density, or at any of the intermediate marginals, PT. We don't have to do it only on the boundary. And so this part is related to a few works that over the years, this is not a popular topic in the diffusion model literature, but there are a few density estimator proposed over the past 2 or 3 years. And so a simple way to think about them is actually to think about this trajectory balance condition. So you have the path measure for the forward process and the path measure induced by the backward process. And these things are in continuous time. So I wrote down the random Nikondo-Dirichlet, and we can actually discretize them. Again, then it becomes the marginals on the boundary and the transition kernels. And the approximate one. If we assume there's a perfect diffusion models, then this would become some of the very easy way to estimate the density under the diffusion model. So essentially, just you put the data density or whatever density on the left, and then you put other things on the right. But again, we know when this would hold. This is not exact. I mean, we won't have a perfect diffusion model, unfortunately, and we do know it holds in the sense of conditional expectation by just doing importance sampling. If you split it up and just cancel it out, taking the integral, if you can trust me, that will give you the density you want. All right. So the reason why we want to talk about this is because if we want to controlling the inference of diffusion model, we do need a way of assessing the density of the marginals easily. All right, so now I want to say, I don't want to sample from the P forward and P backward. Instead, I want to sample from the process with P, with the forward, with the new drift, and the backwards, the new drift. So the reason why is like, people want to do inference time control. Once we train a huge diffusion model with a lot of computational resource, we want to bias it towards a different region of this process. For example, I have a reward function R0. So I want to tilt it some of the, I want to have some human like preferences on some certain part of the space. Or I want to do the product. I have 2 diffusion model. I want to sample from their product distribution, or I want to sample from a annealed distribution. I want to sharper the most or something like that. And again, people wouldn't do it only at the end, do the importance sampling. This will be similar to like the Yazinski equality where the variance would blow up. What people want to do is like sequential Monte Carlo. So we want to define some intermediate marginals. We'll be reweighting on intermediate marginal to keep the variance kind of like smaller. And what does sequential Monte Carlo do? It's actually very simple. So if you want, so here I'm writing t and t prime because it's quite general. It can be between any time. So on the left-hand side, if you want to evaluate some expectation on time xt, so what you can do is like you can start with any time you want t prime, and you starting from there, as long as you can sample, you sample it towards t, and you do importance sampling, and there's a process going forward in time with nu that starting sample from t, and so you can see this like the mu would cancels, and the nu would everything will be integrated out, but only the expectation on the xt boundary, right? So then what you can do this is like you can write down. So this gives you a way to reweight on any marginals, and then if you write on the right-hand side, so the marginals of the annealed marginals that you predefined, it doesn't help you because you still don't know the marginal density. This is where the last slides kick in. So you do want an easy way to estimate the density ratios exponentiated version or the product version or something that related. So you can use the transition kernel to always replace the marginals. So that's the key idea. All right, so I'm almost the end. I want to show a little bit of result. We have a lot of result and we have a lot of other things in the paper, but I don't think I have time to talk about it. So this is one example where you want to design some small molecule ligand of some drugs that binds to multiple protein, right? So so that's kind of like one example of this sampling from the product distribution. And another thing is like you want to do this reward tilting, like all the people, very hot topic in machine learning that people want to fine-tuning diffusion models or just using inference, time sampling method like sequential Monte Carlo to sample from something that you specifically want to maximize certain reward, like make a molecule more like a drugs or more easily to be synthesized. All right, so as I said, there are a lot more in our paper. So you can have the flexible design, proposal, and target process. You, in practice, since you discretize the Gaussian kernels, you have reference process to stabilize the inference. And you can show the inference time scaling behavior. And there's also extension to non-perfect diffusion model under certain condition. And there's also extension to the jump process in discrete space. And also application to learning energy-based model if that's something you care. All right, so, all right, I think that's all. Thank you so much for listening.